Let's look at OpenStack's College Physics, Chapter 16, Problem 18. A diver on a diving board is undergoing simple harmonic motion. Her mass is 55 kilograms, and the period of the motion is 0.8 seconds. The next diver is a male whose period of simple harmonic oscillation is 1.05 seconds. What is his mass if the mass of the board is negligible? So let's write down our knowns and unknowns. We know that mass 1 of the first diver is 55.0 kilograms. We know that the period of motion of mass 1 is T1 is 0.800 seconds. Then we know that the period of oscillation for the second mass, T2, is 1.05 seconds. And we're looking for the mass for mass 2. Mass of the second diver. All right, so I brought here a cheat sheet. We have a whole bunch of equations that apply to simple harmonic motion. And here is a little diagram. There's a diving board that oscillates up and down, and there is a diver jumping up. So let's go through all these equations and see what they mean. So the first equation is Hooke's law. It tells us that the elastic force is proportional to the displacement from equilibrium, and that proportionality constant is the spring constant K. The negative sign stands for the fact that the elastic force is a restoring force. It always wants to bring the elastic thing back into equilibrium. Then we have a set of three equations here that describe the motion. So X is the displacement from equilibrium, and that's equal to the amplitude of the motion, cosine omega t. Taking the derivatives, we get velocity and acceleration. Then here we have the angular frequency of oscillation. So that's 2 pi divided by the period, or 2 pi times the frequency, and that's because frequency is 1 over the period. Then we have another equation for angular frequency, and that is square root of k over m. So since we have a k in this equation, we can assume that we're dealing with a spring-like object. So it's the spring constant divided by the mass that is oscillating. And that is something that we can relate to in this problem. So there is some sort of spring constant to this diving board, and there is a mass that oscillates on that. So keep this equation in mind. Then we have an equation for the energy stored in a spring, and we don't need that for this problem. Then we have this equation. Omega is square root of mg L over I. This is the equation for a physical pendulum. And then the last equation on here is the frequency for a simple pendulum, just a mass hanging from a string of length L. So going back, it looks like this would be a useful equation. However, we're asked to find, or we're given, periods. Well, we know that omega is related to period by this equation. So I'm going to combine these two and work from there. All right, so I'm going to write down omega is 2 pi over period, which means that period is 2 pi over omega. Now we know that omega is square root of k over m, so that will be 2 pi square root of m over k. Now what the two divers have in common is the springboard, and that springboard will have the same spring constant. So when I write the period of the first diver, I have T1 is 2 pi square root m1 over the spring constant of the board. Then for the second diver, I have T2 is 2 pi square root of m2 divided by k. Now, if I divide the two equations, I end up with T1 over T2. A whole bunch of stuff cancels, the 2 pi cancels and the square root of k, but I'm left with square root of m1 over m2. And since I'm looking for m2, I have to square both sides and do some algebra and end up with m2 being m1 times t2 divided by t1 quantity squared. So when I plug in the numbers, I have mass 1 is 55.0 kilograms. T2 is 1.05 seconds. T1 is 0.8 seconds. Quantity squared. So plugging those numbers in our calculator gives us the mass of the second diver to be 94.8 kilograms.